Oh, so we are going to see about crystal field theory. So here we are considering there is a central metal cation which are surrounded by ligands. Central metal cation surrounded by ligands. So which can have like one or more lone pair of electron. So in ligands, okay, so it is like metal surrounded by ligands. So the ligands can be ionic ligands, which are also known as negative point charges, and there are neutral ligands which are considered as point dipoles. So here the central metal ion will be positive charge, okay, and you have ionic ligands which can like have a negative charge, and these are you can also have neutral ligands which can be like a point dipoles. So example like F minus, Cl minus, okay. Here it can be like something like carbon monoxide. So these are behave like a ligand. So in this theory, we don't see like what we saw in molecular orbital. Okay, the orbitals won't overlap or they share the electrons. The metal and ligands don't mix their orbitals or share electrons. So basically telling that there is no overlap. The interaction between them is purely electrostatic, that is 100% ionic compounds. Okay, so these are the salient features of crystal field theory. Okay, so we have a central metal ion surrounded by ligands. Okay, and the metal is basically positive charge, and the ligands okay are like ionic ligands and neutral ligands. Okay, ionic ligands is like negative point charge, where a neutral ligand has like a point dipoles, and here they won't mix the orbitals or share electron. Okay, and the interaction between this metal and ligand, metal cation and the ligand is basically purely electrostatic, and they are ionic compounds. So before going into the, so here what we are going to see is, we are going to see this crystal field theory with respect to two geometries. One is octahedral, another is tetrahedral. Okay, so one is octahedral, another is tetrahedral. And before going and seeing about them, okay, let's have a look how this p orbitals are. So here the major compounds, the compounds that involved in this formation of coordination compounds are transient metal ions, so which has and the octahedral and tetrahedral examples that we are going to is basically based on transition metal ions. So it basically has a d orbital. Okay, so now when you go for d orbital, okay, like we have px, py, and pz, you have 5 d orbitals. Okay, the 5 d orbitals, okay, are dxy, dyz, and xz, and dx square minus y square and dz square. So this is how it looks. Okay, so now here if you see here the dx square minus y square, you see the axis. Okay, and here dz square, you see the axis, whereas here you see xy. Okay, for dxy, here it is along the axis, whereas here they are in between the axis. Okay, so you see these three are in between the axis, whereas these two are along the axis. So remember that. So don't worry about these ones. Okay, right now. So you have 5 orbitals. Okay, so this is the orbitals. Okay, this for these d orbitals have lobes. Okay, which lies in between the axis, and these have lobes. Okay, which is lying in along the axis. Okay, that's a major thing you need to remember, like axial orbitals and non-axial orbitals with the d orbitals. Okay, these are the 5 d orbitals, how it is. Now we are going to see, okay, about these 5d orbitals, how they behave when the ligands approach them. So these 5d orbitals are in the metal cation. Okay, now when the ligands approach the metal cation, what happens to these 5d orbitals? That's what basically the crystal field theory is all about. So now you have this is a octahedral geometry. Okay, this is the octahedral octahedral geometry. Okay, so you have the metal cation at the center, 4 ligands in the plane or in the plane with the metal. Okay, and there are 2 ligands which are in the axial position with respect to this plane. Okay, so it is like to say you have a plane like this, you have a ligand, okay, let's say L, and you have a metal at the center. Okay, so this is like in a square, like a planar structure. Okay, now in addition to these 4, you have 1 ligand above, 1 ligand below the plane. Okay, so this is the octahedral geometry. So remember how the octahedral geometry is. Okay, now the ligands are approaching. Okay, so like the ligands, like you have metal cation like this. So the ligand approaches in from this direction. Okay, now when they approach, okay, here what happens, like they approach along, if you see the geometry with this respect to this geometry, it is approach along x-axis, y-axis, and z-axis. That is, it is approaching along the axis. So now when it approaches along the axis, okay, what is going to happen is that like the lobes which are in the along the axis will going to face the repulsion. Okay, so that is, it is approaching along x, y, z. So which are the lobes along, which are the orbitals along the x and y axis? That is dx square, dz square, whereas these are in between. So if the ligand approaches, okay, the repulsion faced here is huge compared to here. Okay, so the repulsion will be higher in these orbitals as compared to these orbitals. So when there is a repulsion higher in this orbitals, what happens? There happens like energy difference. So the energy difference will occur. Okay, this will be in more higher energy because of the repulsion, whereas this doesn't face that much repulsion, and this will be lower in energy. So if that happens, what happens to this d orbital? So now let's say you draw that diagram. This is the energy. Okay, so let's say like they are like free metal ion. You have 5 d orbitals, they are in degenerated state. Now when they approach, okay, when they approach, the ligands approach, what happens? The total energy will increase initially. Okay, so there is like when they are approaching, okay, the total energy will increase. When they come very close, what happens? The orbital along the axis will see a more repulsion, and because of that, what happens? The energy of these two orbitals which are along the axis will increase, whereas at the same time the energy of the orbitals in between the axis will decrease. That is, this is d z square and dx square minus y square, whereas this is dxy, dyz and dxz. So now this is called crystal field splitting. So this is called crystal field splitting. That is when the ligands are approaching, okay, due to this repulsion, okay, the orbitals which are lying along the axis will face more repulsion and their energy will increase, whereas the one across the axis will be having lower energy. And this energy splitting is called crystal field splitting. Okay, so this is the crystal field splitting. So, and that splitting will be of value delta. Since it is octahedral, I put a subscript O. Okay, stands for octahedral, delta O, because it depends on geometry how they split. So I am putting delta not here. Okay, and these two set of orbitals in this geometry is called EG, and these three sets is called T2G. So this is called as T2G, this is called EG. Okay, there are like term symbols. Okay, one uses this basically derived using the symmetry elements. Okay, so let's we will not be talking about that, but this is called as EG and this is called as T2G. Now, it is also known as crystal field stabilization energy. One can calculate this crystal field stabilization energy, okay, for this compound. That is crystal field splitting or the crystal field stabilization energy. So now let's say I draw only this part, okay. So you have 5d orbitals. This is AG, this is T2G. So now imagine that if there is no splitting happen at all. So this is a no splitting state. Now, how much this is higher compared to this one and how much this is lower compared to this one? Okay, we can say that based on the number of orbitals above and below, the total energy, okay, the splitting here, okay, delta naught, okay, can also given in terms of differential quanta, differential quanta. If we say that it is like something like 10 dq. So either you can use delta naught or one can use 10 dq as well. Okay, like this also. So now if the splitting happens, how much? So this will be minus 0.4, okay, delta naught, and this one is plus 0.6 delta naught. Okay, suppose if you want to give in dq, so it is like 10 dq, right? So if I want to give that, so I have to basically, or I can give into 10, so it is like 6 dq, or I can say this as minus 4 dq. There are two ways to represent this, like either like in delta naught or in differential quanta. So now let's say I have D1, okay. Okay, so now I have one electron in the d orbital. So now they undergo splitting. Okay, so now if I let's draw the figure again, so that like this can be used. So I'm just okay. D1. Okay, so we are going to see for D1. Okay, so D1 I can put one electron here. Okay, now when I go for D2, I can put, so this is T2G and this is EG. Now D2 I can put one electron here. If it is D3, I can put one electron here. Now it is D4. Okay, now D4, the question is, okay, whether the electron can come here or the electron can go here. Okay, the question is whether this electron can get paired, okay, or it can go for rather than EG. Okay, that depends on factor, like two factors, that is how much the split, that is delta naught, okay, and how much energy it is required to pair, that is pairing energy. So that depends on delta naught and pairing energy. This is a crystal field stabilization energy. Okay, crystal field stabilization energy. So there is delta naught and P is pairing energy. So it depends on delta naught and pairing energy. So pairing energy is basically the energy that is required to pair to the two electrons in a same orbit. Okay. So now the splitting is, let's say, such that, okay, the delta naught, okay, not greater than pairing energy. So if the delta naught is greater than pairing energy, okay, so which is the lowest? Pairing energy is the lowest. So it will tend to pair. Okay, so let's again draw like separately two forms. One is just drawing only the splitting states. Okay, let's one electron, two electron, three electron. Okay, so this also like, let's say 3 electron. It doesn't make a difference like until D3. Okay, so until D, let's say common things I will write here. D1, okay, is T2G. I can write it in a simple term. For T2G here, it is 1 EG 0. Okay, there is no electron in 0 for D1. D2, it is T2G 2 EG 0. D3, it is T2G 3 EG 0. Now it only makes a difference when you go for D4. So the question is whether the electron will be going here or here. I said like it depends on delta naught, whether it's a pairing or delta naught is like depends on delta naught and pairing energy. Okay, suppose if the delta naught is okay higher than pairing energy, or the other case the delta naught is less than pairing energy. Okay, so here the delta naught is higher than pairing energy. Here it is delta naught is higher less than pairing energy. So when I go for D4, okay, and I go for D4, in this case, okay, it will prefer, okay, to get, see the delta naught is higher than pairing. So the pairing energy is lower. So it will prefer to pair. Whereas in this case, the delta naught is lower than pairing energy. Okay, so it will go easily here. Okay, it will go easily here, e.g. as the pairing is much higher energy is required. So in that case, Here the D4 is written as T2G. See here 1, 2, 3 and 4, and EG is 0 here. EG is 0 here. Here T2G3, EG1. Here T2G, EG, oh, T2G3, EG1 for D4. Now D5, D6 like this, we can have the same situation. So here it will be T2G 5, EG 0, D5, T2G 3, EG 2. That is 5 electrons. Okay, so one extra you keep putting one electron. Okay, now I go for D6. T2G 6, EG 0. Here T2G 4, EG 2. So that is here, and the sixth electron is comes like now it's all filled, so it will go for T2G and getting paired. Now that D7, T2G 6, EG1, D7, T2G 5, EG 2, sorry, EG2. So one electron here and one electron here. D7, D8, T2G 7, EG2, D8, T2G 6, EG2. So now, if you see here, no, wait, something wrong I did. Oh. 6. Okay. So now, if you see here in D2, it doesn't matter, okay, whether the delta naught is high or low, the configuration is same. The D8, the configuration is same. So it is only matters, okay, whether, okay, delta naught is greater than P or less than P between these states D4 to D7. Okay, so now depending on that, whether if the delta naught is higher, it will tell to get to pair. If the delta naught is lower than pairing energy, it will basically go to the EG state rather than getting paired. Okay, now if you notice here, it is easily getting paired. Here, it is not preferring to get paired, rather it stays unpaired. Okay, like it goes to higher energy level, that is EG. This tells you that the number of unpaired electrons, so for example, even if you take D4, the number of unpaired electrons here is only, let's say, I draw it like this here, 1, 2, 3, 4, because EG is 0. Similarly, if I draw here, 1, 2, 3, 4. Okay, now if you see the number of unpaired electron in this state is, okay, lower compared to higher. Okay, so I call this as a low spin state, or low spin complexes as low spin complexes. This is high spin, the number of unpaired is higher, so high spin state or high spin complexes. Okay, so this way we call these things as a high spin and this is a low spin, because the number of unpaired electron is lower here it is higher. Okay, that's the same reason. So these high spin and low spin state exist only between D4 to D7. After D8 it doesn't make a difference, and if you go for D9, it basically like further like filling these two orbitals, and the D10 is completely full. Okay, so like that we basically have this low spin, high spin complexes. Okay, low spin, high spin complexes or low spin, high spin state. Okay. Now, as I told, it is basically depends on delta knot and pairing energy. Pairing energy is basically like nothing but like it's just the electron. So, but the delta knot can vary depending on the sample or depending on the ligand. Okay, so that are the factors that influence the delta knot. Okay, one with respect to the metal cation. Here in metal cation, okay, depending on number of d electron, okay, if the number of d electron is okay higher, then the delta knot will be lower. Okay, if the number of d electrons is higher, the delta knot is lower. Or if the oxidation state, if we say the oxidation state is higher, the delta knot will be higher. Okay, so if the number of d electron is higher, okay, then the delta knot will be lower. If the oxidation state is higher, delta knot will be higher. So this way the delta knot can be changed. Okay, either depends on number of d electron in given metal cation, or it depends on its oxidation state. Okay, so that's like relative terms. Okay, so like let's say like iron 2 plus and iron 3 plus. Okay, so in the iron 3 plus, the oxidation state is higher. So iron 3 plus will have a higher delta knot than iron 2 plus. Okay, so that's the same idea. Okay, and number of d electron depends on like how like the d electrons are. If the d electrons are more, then the delta knot will be less. Similarly, delta knot increases with second and third row transition metal ions or cations. Okay, as the basically when it go to second row and third row, it is like instead of 3D, it is 4D and 5D. So basically the quantum number, that is principal quantum number, n, okay, increases. Okay, n increases, delta knot increases. Okay, so these are the general factors by which, okay, the metal ion, okay, can have a higher delta knot. Now with respect to ligand, this plays a major role because basically it is basically the same cation. Depending on the ligand, you can have a high spin and low spin states. Okay, so these are the basically based on like chemical experimental evidence. Okay, they basically form a series, okay, called spectrochemical series. It is basically an arrangement of ligands according to the relative magnitude of crystal field splitting. So the ligands are arranged, okay, in a way how the delta knot will increase. Okay, so I'll only write a selectively few things. So the complete list you may see it in your study material. Okay, so for example, okay. So now here the splitting will be lower. Here the splitting will be higher. So it will be like increasing delta. Okay, when you go from this side to this side. Okay, so when the delta knot increases, okay, this side the delta knot will be higher. This side the delta, I mentioned delta because it depends. So depends on delta. Okay, sorry, the depends on the ligand, the delta naught will be varying. So here the delta naught is higher. Okay, so the pairing energy will be lower. So the pairing energy is lower. Okay, here the pairing energy will be higher than delta naught. Okay, because the delta naught is lower on this side. Okay, so now since the depends on delta, okay, here the splitting is higher. I'm going to say these ligands are strong field ligand. These are weak field ligands. So the splitting is less, the splitting is stronger. Okay. Now, as I said, the delta naught will be higher here. It will be lower here. Okay. So higher here means basically the pairing energy is lesser. So it will tend to pair. So if it is pairs, that is what we have is low spin complexes or low spin state. This side we have high spin complexes or high spin state. Okay. So depends on ligand. Okay, so after listing this entire chemical ligands, they saw that like, okay, here these are pi donor and sigma donor. In the middle they are sigma donor, and at the end they saw like they are belong to pi acceptor and sigma donor. So here it mostly decreases the 2Tg energy level. Okay, so basically to say like, let's say you have supposed to be like this, say like supposed to be like this. Okay, this is the delta naught, let's say. What happens here? Okay, here it is basically decreases the 2Tg energy level. Okay, so this is Eg, this is T2G. So here when you have this pi acceptor sigma donors, it decreases the 2G energy level. Whereas here it increases the 2G energy level. So the delta naught will be lower here, the delta naught will be higher here. Okay, so that's the reason you have these are like behave like a strong field ligand. This is a weak field ligand. Even like our hemoglobin, how it works is basically based on this state, like high spin and low spin state. One interested can go and have a look on those things. Okay. Okay. Now these are with respect to octahedral. Okay, one more thing. Okay, one can also calculate the crystal field stabilization energy. Okay, so for example, like we know that they split as T2G, Eg. Okay, so now with the hypothetical state, okay, this is 0.4 minus 0.4 delta naught, 0.6 delta naught. Okay, so depending on the number of electrons, one can also calculate this. Okay, crystal field stabilization energy for this. Okay, so which is I'll give it the formula like T2G. Let's say there are P electrons, and Eg there are Q electrons. So then crystal field stabilization energy is equal to minus 0.4 into P. P is the number of electron in 2Tg orbital, plus 0.6 Q. Q is the number of electron in the Eg orbital into delta naught. Okay, into delta naught. So if you remember, like I also told, delta naught can be replaced by 10 dq as well. One can use 10 dq as well. So I can express these things, same thing in 10 dq also. 0.4 into p plus 0.6 into q 10 dq. I can say it like as well. Similarly, minus 4 so if I bring the 10 inside, minus 4 plus 6 p q dq. So remember how it is like in terms of delta naught or if in terms of dq. Okay, you remember that. Okay, now let's go with the one here. Okay, so T to G, let's say 1, okay, AG 0. Okay, now if I have to calculate, the CFSE is nothing but 0.4 into 1 plus 0.6 into 0, okay, delta naught. So the answer is minus 0.4 delta naught. Okay, this is for D1. Okay, D2 similarly you can calculate, okay, by putting these 2, and D3 it is multiplied by 3. Now when it comes to D4, like I said, you have two possibilities. Okay, so one is high spin, another is low spin. So high spin is like it is T2G. So you have here like number of unpaired electrons more. So it is DEG, T2G3, EG1. Here the number of unpaired electrons will be less. So T2G4, EG0. So that will be pairing. Okay. So now if we calculate the crystal field stabilization energy, so here it will be, let's say I draw the diagram so that it is. In this case, okay, CFSE is minus 0.4 into 3 plus 0.6 into 1 delta naught. Okay, so which is, okay, 4 to 12, like minus 1.2, okay, plus 0.6 delta naught, which is equal to minus 0.6 delta naught. If I calculate this side, okay, so that is CFSE will be equal to minus 0.4 into 4, okay, there are 4 electrons, plus 0.6 into 0 delta naught. Okay, in addition to this, you have to put the pairing energy. So these have one pair. So this is P. So when you write this, you can also write delta naught plus MP, meaning M is number of paired electron. So M is number of paired electron. So if there are 2 paired electron, it is 2p. If it is 3 paired electron, it is 3p, like this. Okay. So in this case, there is only one paired. So it is 1p. Okay. So I can write like this. So the answer is 0.4 into 0.4. It is 1.6 into 0. So plus 0. So delta naught plus p. In some places, they use this pairing energy p as like this, or they don't even use it. So carefully see the answers and like you can choose like some, mostly these questions comes in MCQ or like for 2 or 4 mark questions, like where you can basically solve like find the answer for the crystal. You can maybe asked to calculate the crystal field stabilization. Okay, so next is again. Okay. So this is so far for a octahedral complex. Okay. Now let's move on and study about the tetrahedral complex or geometry. So in octahedral complex, you saw that like the ligands are approaching along the axis, and hence the basically the energy of this EG orbital increases, and the splitting is happening at the same time, and T2 will be lower in energy. Okay, whereas in case of tetrahedral, okay, let me put the diagram. So this is how in a tetrahedral. Okay, here in tetrahedral, the metal ion is at the center. Okay, and the ligands are approaching along in between the axis. Okay, the ligands are approaching in between the axis, not along the axis. Now it might be clear like for you. Okay, so I can write like this, like Ml 4 ligands. Okay, charge can be N plus. Okay, so now the ligands are approaching in between the axis. Okay, so the same way the total energy of the d electron will increase when they are like nearing by. When they are close, okay, there happens a splitting. So which one faces the more repulsion? The one which is in between the axis. Okay, so in that case it will be the d xy yz. Okay, xz, they will be higher in energy, whereas here the dx is the in between axis. Okay, that is dx square minus y square and dz square will be lower in energy, whereas dxy, dyz and dxz are okay higher in energy, because these will be more repulsion than this one. Okay, now the energy difference between these two, okay, is given as delta, but with the symbol subscript as T. Okay, there you use delta naught. Here it is delta T. So do you remember the difference? Delta T and delta naught are different. They are not the same. Okay, but they can be related. Okay, that I will come to that shortly. Okay, so you have delta T, that is a crystal field stabilization energy for a tetrahedral complex. So now we try it again. So this is the non-splitting state. Okay, so total is delta T, and how much this is away from the non-splitting state, like if it is just opposite of octal. This is 0.4. There it was minus 0.4 in the bottom, so now it is on the top, minus plus 0.4 delta T and minus 0.6 delta T. Okay, so now if I have to calculate the crystal field stabilization energy, okay, so now, and also this is like this is a set of orbitals. This is by given with the term symbol, okay, E, and this is given with the symbol T2. Okay, so here we are not using G. Okay, so remember that. So here we use T2 and E. Okay, so this one is dx square minus y square dz square as E, and the term symbol for this one dxy, yz and xz as T2. Okay, so now you have E and T2 is a, and the number of unpaired electrons, number of electrons can be P and Q. So if I calculate the CFSE here, okay, it is minus 0.6 into P plus 0.4 into Q delta T. Okay, so this is the formula. Okay, one can use this formula and calculate. Now, before going into the calculation, let me also tell okay, compare it with the delta T and delta naught. Okay, so we have a situation depending on ligand, we have tetrahedral and octahedral complex, right? So let's say this is a free ion. Okay, in octahedral environment, okay, the splitting will be like this, where you have the Eg on the top. In tetrahedral geometry, it will be like this. This is delta naught and this is delta T. So here it is Ml4, that is like 4 ligands approaching a metal ion which has oxygen state N plus, whereas here it is 6 ligands. Okay, so there is a difference in ligand itself. Okay, so the number of ligand, based on number of ligand. Okay, so ligand based on number of ligand, you have 4 by 6. Okay, that is equal to 2 by 3 of octahedral. So when you compare to octahedral, it is 2 by 3 lower. Okay, so 2 by 3 lower. Now, in addition to this, okay, the direction of ligand approach does not coincide with d orbital. So it is not like perfectly aligning with the d orbitals when they approach. So there is a this mismatch. Okay, and that contribution is of 2 by 3 factor. Okay, so total delta T, okay, is approximately lower by 2 by 3 from the number of ligands and 2 by 3 from the direction. Okay, with respect to octahedral. So delta T is approximately equal to 4 by 9 delta naught. So in some problems, okay, when you are asked to solve, you have to, for example, like when you are in a descriptive no problem, you can directly calculate whatever the delta T or delta naught. But when you in MCQ, let's say you have asked to calculate for tetrahedral complex, okay, and or it may be given like such that there are 4 ligands. Okay, the formula might have given, and you should think that it's a 4 ligands, so it is a tetrahedral complex. Okay, there is another geometry also, square planar, but since your syllabus is like tetrahedral, we'll limit to that. Okay, so depending on that, the delta, it is for like tetrahedral. Suppose the answers are in delta naught, not delta T, then you have to use this formula, okay, to calculate the delta in terms of octahedral, okay, delta naught. So okay, so you can do like regular, like how you calculate the CFSE for. So for example, you have the CFSE, right? So CFSE is equal to minus 0.6 P plus 0.4 Q delta T you can calculate in the same way. Then to convert that into delta naught, you can calculate this and multiply by 4/9 delta naught. Okay, so either you can do calculate like this, then instead of delta t you can put 4/9 delta naught. Okay, or you can straight away use the simple formula that, like, so if you bring 4/9, it will be like 0.27 t plus 0.18 q delta naught. Okay, so it is up to you or convenient. Okay, but make sure that you don't do anything wrongly. So if you want to go ahead with delta t, like simple as that, okay, calculate it. Okay, if they don't bother you to ask delta naught, then you don't need to bother at all. Okay, suppose if they ask you to tell in terms of delta naught, then you have to bring this into picture and multiply it. That is very simple. Okay, so you can remember like this based on the number of ligands. So if you like, generally it goes like you have 2 ligands, okay, then it is 0.4. Similarly in octahedral also there was 2 ligands, so it was 0.4 in the down. Okay, and you have 3 ligands, okay, and it is minus 0.6. So like it's like number of ligands in multiplied by 0.2. Okay, now as we see here, the delta naught, okay, the delta t is basically 4/9 delta naught. So delta t is obviously lower than delta naught. Okay, so hence there is no low spin. So the delta t, okay, is approximately 4/9 delta naught. So the delta t is lower than delta t. Okay, so that implies that like there is no low spin state because the delta t is lower than pairing energy. Okay, the delta t is always lower than pairing energy. There is no low spin state. It is always high spin state. Okay, so that is for D1, it is like this. Sorry. Is E2, then D3. So now, similar to that, we had a question whether it will go here or it will go here. Here it won't go and get paired because the delta T is lower than pairing energy. Okay, so it will directly goes to the T2. So it is E2 and T1. Okay, so this is how it is in the case of tetrahedral. There is no there is no low spin state. It is always high spin state. Okay. Let's calculate the CFSE. So like here, for a D1. CFS is minus 0.6. Okay, number of electron in the E, so it is into 1 plus 0.4. Number of electrons in T2, it is 0 delta T, so it is 0 minus 0.6 delta T. So this term is 0, so it is minus 0.6 delta T. So you can also convert it into terms of delta naught. So for that, minus 0.6. Okay, delta T should be replaced by 4 by 9 delta naught, which will be around minus 0.27 delta naught. Okay, so like this, one can interchange from delta T to delta naught. So similarly, D2, okay, I can go with E 2 T 2 0. Okay, here let's say like I use the formula CFSE directly, or instead of like multiplying here, I can directly use, okay, like, or let's say like I go with the simple, or okay, seven P, so P is 2 plus 0.18, okay, into 0 delta naught. So it is not necessary you should report in delta naught if it is not asked. Okay, so you can represent in delta T itself. Okay, so it is minus 0.54 delta naught. Okay, so this is the how you can calculate the crystal field stabilization energy. Okay, next, any doubt here so far, students?
No doubt, sir. Sir, whether you will share the recording link after class, sir?
Yeah, I have to edit and I'll show you. Okay.
Okay, sir. It will be helpful, sir.
Yeah. But you are taking notes, right?
Yes, sir. I am taking, sir. If I have some doubt, so that I can watch it again, no, sir.
Okay. Okay. So next, the magnetism. That is basically going to talk about the magnetic properties. Okay. There are different ways one can measure the magnetic properties, okay, of a material. There are like a VSM method, Guy balance. Okay, the VSM method is quite often used, and VSM and SQUID. Okay, there are like recently advanced method where we basically put your sample in magnet and by like trick called SQUID, and or by vibrating you can measure it in a VSM. Okay, there was before this there was like a method called Guy balance, basically where they basically measure the weight of the sample with and without magnetic field. So basically what they do is like in the it's like a laboratory experiment as well. One can like set up in a lab also and try to measure it, but it can be only done at room temperature and see the magnetic moment. Okay, so now in this case they have put a magnet, okay, and they put the there'll be like a thread, nylon thread, which is connected to a glass rod, and the glass rod is connected to a Guy tube. Okay. So you have a glass rod and you have a Guy tube. Okay. In the Guy tube you have the sample. Okay. So you can keep the sample in the coil tube and measure. So this is connected to a balance. Now what they basically measure is measure the weight for empty coil coil tube, then weight with sample, then both things with and without magnetic field. Okay, so from here they basically calculate the moment. Okay, so this is where experimentally do it. One can also calculate it, okay, or based on what the value you get, or what is the metal ion, because when you measure the sample, mostly you know what is the metal ion present. So from based on that also you can calculate what is the magnetic moment. Okay, so that can be calculated by a formula called mu. Okay, here it is magnetic moment. Okay, and this formula is called spin only magnetic moment, because we only use the number of unpaired unpaired electron in the metal ion. Okay, so this is spin only magnetic moment. Okay, so this is here n is the number of unpaired electron. Okay, so now in this case you have let's say I give an example. Okay, let's say we have a complex cobalt F6 3 minus. Okay, so cobalt is, okay, here F is minus. Okay, we know like a ligand, when we talked about ligand, F is minus, like negative charge ligand, like in F minus. So you have 6, so it is 6 minus. Okay, so there is 3 minus, and so this is total charge. Okay, 3 minus. So this is, okay, in this case it will be, you don't know the x, let's say put x plus 6 into minus 1 equal to minus 3. So it is minus 6 3. So x equal to 6 comes this side, so x minus 3, it is 3. So the oxidation state of cobalt is 3 plus. Cobalt element will have D7. Okay, now here it is, when it is cobalt, these 2 plus. Okay, when it is cobalt 2 plus, is again D7. The reason is, okay, you have the 4s2. Okay, when you have a cobalt, you have this is 3d7, that is 4s2. So these 2 electrons will go, so that is cobalt 2 plus, and this is D7. Okay, and when it is cobalt 3 plus, one more, the d electron will go away, then it is D6. Okay, so you have D6. Okay, so now what is the geometry here? You have 6 ligands. Okay, 6 ligands means whether it's octahedral or tetrahedral. Whether it's octahedral or tetrahedral, students?
Octahedral.
Octahedral. Okay, so you have cobalt F6, okay, 3 minus, okay, which is in octahedral. So the CFSC, sorry, you can also calculate CFSE for this. Okay, that is also a good practice. Okay, so let's say D6. Okay, so you have states like splitting like happening like this in the T2G EG. Okay, so you have 1, 2, 3. The third electron will go here or here. What is the F minus? Is a strong field ligand or weak field ligand?
Weak, sir.
Weak field ligand. So it will
So
go,
EG.
it will go to EG. Then comes here. So D6. Okay. So now you can calculate CFSE and calculate the spin only moment. So how many unpaired electrons are here?
In T2G2, sir.
Total, the complex, how many unpaired electrons are there? You have to use that. Okay. The formula root of n into n plus 2 both magneton. And the crystal field stabilization energy, you know, like it is for an octahedral complex. What is the formula?
Minus 0.4.
Minus 0.4. Let's say Pn. So minus 0.4 P plus 0.6 Q delta naught plus M. Okay. So everyone calculate and let me know what is the value.
Spin only magnetic moment mu is equal to root 24, sir. 4.898.
Okay. What about CFSE? So minus 0.4 delta naught. What about here? How many number of pairing electrons are there?
1.
1. So one can give P. M is equal to 1 is P. 4 electrons, 4 into 4 plus 2 Bohr magnetons. The total answer will be 4.9 Bohr magneton. Okay. Okay. So now let's say for a same cobalt complex. Okay. But in this case now strong field ligand. Okay, now you do by yourself and calculate and let me know. What is the CFSE? What is the spin only magnetic moment?
So CFSE is minus 2.4 delta O plus 2P.
Okay. What is the charge of cobalt? What is the oxidation state of cobalt?
+3, sir.
Plus 3. Plus 3 means again D6 only, right?
Yes, sir.
So if it is
Yes, sir.
D6, okay, I told you like this is a strong field ligand. So what happens?
So
D6.
pairing will take place, sir, in
Yeah,
T2G.
pairing will take place. So if you pair it, what is the CFSE?
Minus 2.4 delta O plus 2P, sir.
Okay, not 2P, 3P, right? 3
Yes, sir. 3,
unpaired.
sir.
So that is minus 2.4 delta naught plus 3P. Okay. What about mu as the spin magnetic moment?
0, sir.
It will be 0. So the mu s
0.
is, there is n equal to 0. So mu s is equal to 0. So it is diamagnetic. Now calculate cobalt okay, let's say cobalt 3 plus in tetrahedral field. Calculate the CFSE and magnetic moment. So you have to use the formula that you use for tetrahedral. Okay, you can use delta T itself. You don't need to worry about converting into delta naught. Use this formula itself. The delta T is lower than delta naught. That is how much lower? Delta T is basically 4/9 of delta naught. So this delta T is lower. So there is delta T is always lower than pairing energy. Okay, so there is no pairing will happen first. It will always go to the E. After filling the E, it will always go to the T2. Okay, it's always high spin. There is no low spin state in a tetrahedral complex. Minus 0.6 delta T plus 1 P. Okay.
4.898, sir. Root 24. 4.898.
Okay. Now, number of unpaired electron 2 means it is 2 plus 2, 4, root of 8. Okay. Similarly, here, if it is number of unpaired electron is 2 means 2 half. Okay. So 2 into like 1. So 4 into 2 is root 8. Okay. So it's just that how we calculate is different. Here, it is you consider the S. Okay. Where S is equal to N into half. Okay. Don't in multiplicity is calculated with the same S. Okay. But it is 2S plus 1. Okay. The spin multiplicity is 2S plus 1. So S is again the same. S equal to number of unpaired electron into half. Okay, so this obeys with the first row transition metals. Okay, we are not going to see about the second row, but however the formula there it is different. Okay, so there is a like orbital as a spin orbit coupling also happens. So the formula will be 4s s plus 1 plus L into L plus 1. This is just for your knowledge only. You don't need to. You may not have problems based on this. So S is the spin quantum number and L is the orbital angular quantum number. Okay, so this is where you have a spin orbit coupling in the second row and